found over the years that I've been the SI for 2742 is where most people struggle is with the labs because you'll be expected to be doing some programming beyond what you did in 2741, and people just like to have a little extra help, a little security blanket. And so a lot of times I go over the labs on the Mondays that y'all are going to do on Tuesdays. It's best if you have an idea what you're supposed to do before you come here. And I don't necessarily do everything out completely, so it's not like you can come here and know exactly what to do. I'm just going to get you started on it and help answer questions about it. And then usually on the Wednesday sessions, I'll go over things like questions about the homework or topics from in class or anything like that. All right, so Lab 3 that y'all are going to do tomorrow is a Mersenne number detector. And the first thing we want to do is talk about what a Mersenne number is. So a Mersenne number is a number of the form 2 to the n minus 1. And just a note, many are primes. So you may hear the term Mersenne prime. So not all Mersenne numbers are primes, and not all prime numbers are Mersenne numbers. But if someone refers to a Mersenne prime, they're talking about a number that is both prime and Mersenne. And that's what I've worked with before, so I think I might have titled my worksheet Mersenne primes. Even though you're not detecting those, you're detecting Mersenne numbers. So let's take a look at what these numbers would look like, and this would be for n greater than 1, greater than or equal to 1. So if n equals 1, we would have 2 to the 1 minus 1, which would be 1. And if n equals 2, we would have 2 squared minus 1, which would be 4 minus 1, which is 3. So what would we have for n equals 3? 2 to the third minus 1, which is 8 minus 1, which is 7. And n equals 4. Sixteen minus 1, which is 15. Okay, so those are the first 4 Mersenne numbers. And if you look at your lab says the purpose of this lab experiment is to apply knowledge of combinational logic circuits to the design of circuits, or the function realization includes multiplexers and decoders. And then it says we have a Mersenne number is a form of 2n minus 1 for some integer n, and we'll be looking at 4-bit Mersenne numbers. And so we're going to have 4 bits labeled x3, x2, x1, and x0, where x3 is the most significant bit and x0 is the least significant bit, labeled MER. So are y'all familiar with those terms, most significant bit and least significant bit? Yep. Okay, so we'll have our numbers will be x3, x2, x1, and x0. And I would like y'all to look at the following numbers that I'm writing up here and tell me what they have in common. There's lots of different things you can tell me that they have in common, but what do these 4 numbers have in common?
All of their ones are on the least significant bit and all in the same row without changing the 0.
Right. And I don't know like a really clear, succinct way to say that. Maybe what you said was as good as it gets. So what did you say?
All of the ones are on the least significant bit, and the ones beside it are not zero.
Okay. So the ones are all on the LS bit side, maybe. So they all start with zeros and continue until you get to a 1. And then the digits are all 1. So it's zeros until you get to a 1 and then ones. So that tells you that we now would know if we had to make a Mersenne number that was, higher order, had more bits, we know that without figuring out what it is, that this would be a Mersenne number. We don't know what it is, but it would be 1. And just in terms of binary numbers, why is that going to be true? Why would we have that format? And based on what a Mersenne number is. So a Mersenne number is 2 to the n minus 1. Yeah.
2 to the n would be like, it would be like a binary number with only 1 somewhere. And so if you subtract 1, it takes the position to the left of that. And it'll flip all of them to 0. Because a 2 to the n is like a perfect number.
Right. So 2 to the n would have a 1 in the nth spot of the binary number, and everything else would be zeros. Because the binary number has the digits, this is 2 to the 0, this is 2 to the first, this is 2 squared, this is 2 to the third, and so on until you get to 2 to the n. And so 2 to the n would be a 1 followed by all zeros. And so if you subtract 1 from that, then you'll get zeros and then all ones. So that's why that would be a Mersenne number. Okay, so now if you have a copy of the handout, then what I would like you to do, and if you don't have a copy of the handout and would like one, I can print out a few more. It's not that exciting, but I can print out some more if anybody wants one. It has a truth table for you to fill out that shows for the values of x3, x2, x1, and x0 whether or not it is a Mersenne number. So would anybody else like me to print out a copy of the handout? 1, 2, 3, and it is on Moodle as well if you want that, but I will be happy to print it out. So I'm going to do that. And while I'm doing that, y'all just go ahead and, those of you who have it, fill in the table. Just how would our truth table look if we were trying to get a Mersenne number detector? And yes, I am lazy, but it is also true that I have serious joint issues and connective joint disorder. So I often ask people, do you mind like getting up and getting something? Part of it is just strict laziness. But if you're wondering why I'm always asking people to get things from
There's only an 8 input one. So you can't use only one multiplexer.
Did
You
we
can.
have stuff that we can?
Yeah, but I give it a
You can use just one
Easy
ASIC.
to explain.
Oh, 'cause it has two
guys. Yeah, so
How do you use the decoder on this?
I don't know, I'll see. I just picked one up. Is that a decoder or not?
this is cool.
Decoder.
I mean, I went through her off sound, I was just having something on.
You shall ask her how we make this work.
Yeah.
I'm interested in that.
Unfortunately, I just ran out of printer paper, so those of you who asked for one, get one, but I don't have any extras, so raise your hand if you asked for one, just a minute there. And if you don't have one, it's fine, everything we're doing, you can do on paper. So, if you just came in, what we were doing is we were going over what Mersenne numbers were. And Mersenne numbers are numbers that are of the form a power of 2 minus 1. And when you look at them as binary numbers, they'll have leading zeros and then ones at the end. So your first Mersenne number is 0001, then 0011, then 0111, and then 1111. Those are the first four Mersenne numbers and the ones that you can make with 4 bits. And what we were just doing is filling out a truth table that would have us figure out which ones are Mersenne numbers. And my handwriting is terrible, so just make sure you stop me if you can't read something that I've written. These are just the binary numbers from 0 to 15. And you should get that 0001 is a Mersenne number, 0011 is a Mersenne number, and 0111 is a Mersenne number, and 1111 is a Mersenne number. And the rest are all going to be zeros. And we will come back to this truth table. It will help us as we're figuring out how to use decoders and multiplexers to set up our circuit. And I believe this is part of your pre-lab to turn this in, I think. Let's see, is that correct? Turn in a truth table. Pre-lab. Version number. Maybe not. I don't know why I thought it was. I thought it was. Okay, now one thing that people have had questions about on the lab that was like this in the past, this is different from previous years, but they had similar ones. Notice that for your pre-lab, you do have to draw out all three types of circuits. In the lab, you'll only have to do two of them. You only have to build two of them. You'll have to build all three. Okay, so for our next step, what we'll want to do is, if we're just going to use any gates, any of the old gates like we used to use in Digital Logic 1, we would want to simplify this using a K-map. And if you have the worksheet, you have a K-map handy. And if you don't, you can just draw one. And I'll do it the same as on this one. It doesn't say here. So does your K-map have X3, X2 here, and X1, X0 here, or does it not say?
It doesn't say.
Okay, that's how I'm going to do it. So most significant bit here, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, and 1, 0. So now we want to fill this in based on our truth table that we just had. So I want y'all to try to do that on your own, see if you can remember from Digital Logic 1. If you have any questions, you can ask, and I will show you in case you have forgotten. But I want you to give it a shot first. So we want ones for these 4 rows. And this bottom row is the easiest one. That's where they're all ones. So that's going to be 1, 1, 1, 1. So that's right here. And then this first one that has a 1, X3, X2 is 0, 0. X1, X0 is 0, 1. So 0, 0, 0, 1 is right here. And then the next one we want is 0, 0, 1, 1. So we have 0, 0, 1, 1. And then the number 7, and by the way, let me just label these, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And 7 is 0, 1, 1, 1, which would be right here. So what's going to be the most efficient cover for those? Remember, we have to have, our groups have to be powers of 2. So you can have a group of 1, 2, 4, 8, or 16. And you want to have you want the groups to be as big as possible, and you want to have as few of them as possible.
Just group. So, yep. I was going to say just group the 2 ones.
Which group of 2 ones?
The left side and then like the lower middle.
Right here and right here?
This one.
Yep, I think that's the best one. Yep. I mean, there are other ones that you could do, but they're not going to be the most efficient, and you want to be the most efficient because you have to build this in the lab. You can put zeros in the other places if you want to, but I don't want to. Okay, so now to figure out what this corresponds to, remember this is x3, x2, so x3, and it's x3 bar and x2 bar because they're both zeros. And then the numbers on the side are x1 and x0. And we see that x1 can be 0 or 1, but x0 is always 1. And so for this row right here, that would be x3 bar, x2 bar, and x0. Or, now if we look at this row right here, we see that x1 and x0 are both 1. So x1 and x0 are both 1. And x2 for both of these is 1. So x2, x1, x0. So that is the simplified expression that I got. Let me see if that matches. Yep. All right. So now let's think about how we would build this as a circuit. So we have 3 inputs. Those are going to be the little switches on your board. And this you can draw this. If you have a worksheet, you can draw it just for your reference. There's a nice little box for it. You don't have a worksheet, you can just draw it. It's not important. So your inputs are x3, x0, x1, x2, and x3. And we will need an AND gate. Let's see, what do the directions tell us we can use? Any gates available in the lab. So I would prefer to use a 3-input AND gate and an OR gate and an inverter. And so the inverter, that's a NOT gate. So I need to get the NOT of x2 and x3. And I will need to AND those to x0. And I need the AND of x2, x1, and x0. And I need to OR those together. And that will be my output mirror. So now let's talk about how we would lay this out on chips. So we'd have 3 chips. Actually, I'm going to cut and paste. If you need to find them, if you go to your class, and you go to lab resources. That's not going to show up in the video, but it's a link over on the side, lab resources. You should have chips available in the lab. And so we want a 74X04. Somebody write this down. So 74X04, a 74X11, and a 74X32. Okay, so I have downloaded, you also would find the data sheets there, and I have downloaded all of those, so I have those. Okay, so which ones did I say we needed?
04, 11, and 32.
04, 11,
And 32.
and 32. Okay, so this top one is my inverter. This next one is my 3-input AND gate, and the bottom one is my OR. And I'll label them here. One, two, three. And here I'll put a 1 on each of these because that's going to be my inverter. And I'll put a 2 on each of these because those are my AND gates. And I'll put a 3 on that because that'll be my OR gate. And then my inputs into, I will have X0, X1, X2, X3. X2 and X3 are going into the NOT gate. So X2, I'll have it go into 1A. I'll have X3 go into 2A. So I'm going to put right here for X2, I'm going to put 1A and then in parentheses 1 so that I know it's pin 1, and then 2A and then in parentheses 3 so I know it's pin 3. And the pink 1 on here tells me it's with chip 1. And then the output from 1A is 1Y. So that's 1Y. And then I'll put in parentheses that that's pin 2. So I know how to connect it on the breadboard. And the output for 2A is 2Y. And that's pin 4. So I know how to connect those onto the chips on the breadboard. Okay, so now I have my 3 inputs into this top AND gate, and those will be 1A, 1B, and 1C. So 1A, 1B, and 1C. And those are pins 1, 2, and 13. So that's, let's see, so that's X0 is going into pin 1. X1 is going into pin 2. And X2 is going into pin 13. And then we have our second AND gate. Oh, and our output for that is going to be 1Y, which is pin 12. Then our second AND gate will be 2A, 2B, and 2C. So it'll be 2A, 2B, and 2C. And those are pins 3, 4, and 5. And the output is 2Y, which is pin 6. And those were X0, and the knot of X2. So the knot of X2 was 1Y. That's the output. See, 1Y right here is the knot. This is going in, so we're going from here to here. So I'm going from 1Y into 2B. And then the last one was 2Y, or pin 4, is going into pin 5. So this one is going into pin 5. And I'm afraid this is about as neat as my circuits ever get. This is the neatest you're ever going to see. So, all right, and then lastly, we have our OR gate. We only need 2 inputs for that, so we can use 1A and 1B. So I'll have 1A, and that's pin 1, and 1B, and that's pin 2. And those are coming from pin 12 and pin 6 from this one. And this is being recorded, so I will post it all to Moodle, so you can come back and look at it if you want to. And then my output is going to be 1Y, pin 3. 1Y, pin 3. And that's going to be MIR. And that's what you're going to attach to some sort of LED signal. So these are going to be switches, and this will be an LED. There are certainly other ways to do it. This is not the only way to do it. That this most likely works. I usually, like I'm not demonstrating it here right in front of you, so there's always a possibility of a mistake, but it gets you the idea. So that's how you would do it using just your standard AND and OR gates. So the next thing we have to look at is the multiplexer. Because before we go on to the multiplexer, because the multiplexer and the decoder are where things get a little bit tricky. Up to now, this is all stuff kinda you could have done before. So any questions on any of this? Okay. Okay. Speaking of which, I'm actually going to stop the recording and start a new one just so it's not so long.